Good afternoon, ladies and gentlemen. It's a great pleasure to introduce our today's speaker, Professor Michele Parrinello from ETH Zurich and Università della Svizzera Italiana in Lugano. Professor Parrinello is one of the founders of the field of computational material science and one of the best-known, most impactful physicists today. He has graduated from the University of Bologna and wrote his thesis in the field of nuclear physics, after which he switched to the field of then emerging field of atomistic simulations, the field in which he has produced works of tremendous impact. He worked at International School of Advanced Studies in Trieste, after which he moved as a director to Max Planck Institute in Stuttgart, Germany, and then moved to ETH Zurich in Switzerland, where he is a professor since 2001, where he also held position of the director of the Swiss National Supercomputing Center, and where he has a very vibrant and famous research group. Professor Parrinello is very well known for such fundamental developments as the Parrinello method, which married density functional theory and molecular dynamics. His paper about the Parrinello method is the 5th most cited paper ever published by Physical Review Letters. Another famous contribution is the Parrinello-Raman method in molecular dynamics, as well as many other developments in molecular dynamics simulation methodologies. And more recently, the plethora of methods based on ideas of metadynamics, which he has pioneered. The impact of his works is enormous and ranges throughout the field of material science, chemistry, physics, geosciences, planetary sciences, biophysics, biochemistry, pharmaceutical sciences. His H-index is 114, which is one of the highest among all scientists living today. It's a great pleasure and honor to listen to his talk today, and let's welcome him for his lecture.
Thank you for the invitation. It's a pleasure being here. And today we'll go through a tour from my eyes. I've seen from my eyes of the development in atomistic simulation. And of course, being delivered by me, there will be strong bias towards what I've done, but really it's been the achievement of these decades have been the work of a generation of scientists. Okay, so the talk will be very general because I thought the audience would have been rather mixed, and so some of you might get bored now and then, or maybe all the time, depending. Okay, so at the basis of what I'm going to do, there is the famous Moore law on the development of computers in the last decades, which follows an exponential growth, and this is taken from the top 500 site, with a site which lists the 500 most powerful computers today, and as measured by this trend, one sees this continuous and apparently unstoppable growth in computer power, which is available to scientists. And since I mean, really, it's hard to measure the power of computers because this top 500 is based on essentially linear algebra kind of test. So real problems are really more complicated, and so a better way of measuring the progress is given by this slide, which has been kindly given to me by Thomas Schultes, the present director of the Swiss Supercomputer Center, which shows the speed on top application. As you might know, that there is a yearly prize for high-speed, high-performance computing on physical, on real applications, and it's given to the best program for the years. The speed is measured on real application. You see that it's not only our ability to solve linear algebra problems, but also on real problems. There's been continuous growth. Part of it, of course, is due to technology, but also a lot of it is due to clever algorithms. One aspect of the computer development which needs not to be under-evaluated is the fact that that's the growth of the top computers, but also the scientists that have not access to top-of-the-range computers, they nowadays have computers as powerful as the supercomputers of years back. And if I look back to my own experience, I can see what has happened to me. This is a computer in Trieste when I was at the time, where we developed the Parrinello method, and this is the cyber available in those years where the first tests were made. And nowadays, the same calculation that was done on the computer can be done on a mobile telephone. This looks big on the screen, but actually it's a mobile telephone. It's one model of Nokia model where which supports the Linux system. And so Professor Marzari from EPFL made this little movie that shows here, if you look at that, that's the output of the code. And for those familiar with CPMD, they will recognize the output of a CPMD. So calculation that needed cupboards of computers and a lot of power can be done on an handheld telephone. Okay. And of course, this is probably known to all of you, that this has led to a real revolution in our approach to science. And so together with theory and experiment, with nowadays computer simulation as it's a new way of doing science, and exponential growth one allows to face more and more complex problem. And essentially, there is no field which has not been affected by computer simulation. Whether we know social sciences, finance, unfortunately, medicine, material science, and so on and so forth. And this has become now a platitude that science stands on three legs: simulation, theory, and experiment. Okay, now there are many kinds of simulations. And what we have been doing over the years is to do atomistic simulation, starting from an atomic description of the matter to derive its properties. And why do we do that? So experiments provide us with a limited number of parameters, and so we can complement the experiment and get insight in what the real system does. experiments that might be difficult, expensive, or dangerous. If you think of radioactive material, or even more simple elements like beryllium is very poisonous, and chemists don't like to work with beryllium. And on the computer, it's just as poisonous as carbon. Huh? So can predict new phenomena. It's a form of virtual microscopy. And nowadays, there is this trend towards all kinds of omics. So to explore very large number of possibilities on the computer, to reduce the number of experiments, or to find materials or drugs with special new properties. So as a tool for discovery. The basis is very simple. So we start with Newton's equation, and where we describe the atom as classical particle, and we solve on the computer Newton's equation once we know the potential of interaction between the system. And the system is basically represented as a system of interacting spheres. This is a beautiful STM picture, and I bring it up because that's the silicon surface. I think the silicon 111. And I bring it up because one of the inventors of this beautiful microscope was a close friend of mine, Annie Rohrer, and passed away last year, very sadly. But basically, the idea is that for many, many intents and purposes, atoms can be described as little spheres because of the electronic density concentrate around the nuclei, and if you try to bring together two electronic the cloud of electrons from two atoms, that will lead to a strong repulsion. These things was clearly understood a long time ago, and in the view of many of us, the beginning of molecular dynamics for the simulation of materials really started with this paper, which is now 50 years old. And there will be a conference this year in India to commemorate this event. And it's a paper by Anis Rahman, with whom I had the great privilege of working when I visited my visit to Argonne National Laboratory long time ago, say. Huh? And this simulation was a simulation performed on argon, and the interaction in this case is simple to describe. So if I look at two argon atoms, when I bring them close, there is a strong repulsion, as I described earlier on, to the overlap of the electronic clouds, and the long range, there is the van der Waals interaction at long range. And this was a simulation of atomic system, the pair correlation, lots and lots of properties. So really, Anis on that paper showed the way for the simulation of condensed matter, the language, the method, the technology, the program. It's all coming from there. And I mean, the program that we use, the source, including the program Martin Karplus, the program of Uzi Landman, and my own code, everything comes from the work of Anis, who was very generous with people and gave away all his codes and his knowledge freely to everybody. Okay, so of course, argon is a very simple thing, but the construction of interaction potential over the years has been refined. And for instance, for protein, the interaction potential is this structure where there is an internal energy, the bond stretching, bond bending, torsion, and also there is the non-bonded interaction where atoms interact. Atoms are here, for instance, for this little molecule, which is a urea molecule, are connected among themselves by chemical bonds, but there is a non-bonding interaction between, say, this urea molecule and the water molecule, which is described with the Lennard-Jones kind of potential, plus, if needed, some Coulomb interaction. Okay. In its birth, this way of doing science was not very much appreciated by many, and it remained for decades a pariah and snapped upon by other more noble form of theoretical physics. But things have changed, and I think the first sign that things have changed, in my view, comes from this movie. This movie represents a protein, which is called aquaporine, and which is like a channel through which water molecule can percolate in and out of the cell. The membrane is not shown here. The protein is represented in this stylized manner, and you have this water channel. And the reason why I bring this simulation to your attention, simulation which has been performed by Klaus Schulten, that a few years back, a Nobel Prize was awarded to Peter Egor for the discovery of this structure. And in the Nobel Prize nomination, one of the supporting evidence for the validity of the structure resolved by Egor was precisely this simulation. And so it's an indication of attributing the simulations a kind of epistemological dignity, cognitive dignity. Okay. And of course, you are all aware of the Nobel Prize that, of last year. Okay, so from the humble origin of argon interaction, I think this kind of simulation has gone a long way, and of course the validity of what comes out, it all depends on the potential energy surface, and these empirical potential are of course efficient, but they cannot describe well physics, chemistry, complex chemistry, and subtle effects, as I will show you later on. And for instance, if you have a system like this is a DNA, a strand of DNA, and if the radiation comes, one electron is ejected out, you get a radical, and this radical can move along the strand, and simulating this phenomenon with classical means, or with something which is very localized in one place, in a QMMM kind of things. It's not really realistic, and you have to treat the whole system. And in fact, if you do, you find features that were not described earlier on. Okay. And that implies, if you want to do that, it implies bringing into the picture not only the ionic position, you want to go deeper in the description of the atoms. So you describe the atom as nuclei and electrons, not any longer as small spheres interacting. And treating the electrons requires solving the Schrödinger equation. The electrons are highly quantum particles, so they require quantum mechanics. And so one can use either Schrödinger's equation or more practical for the large system that we use, people tend to describe the electronic interaction through the density functional theory. And the first time when we tried to do that was now almost 30 years ago in Trieste on that computer that I showed earlier on, and where we combined MD, so dynamics for the ions, with electronic structure calculations, and this allows us to calculate without fitting parameter. Density functional theory has its limit, but it has accuracy and predictive power in many cases. And we can have access to properties that depend on the electrons, like infrared, the Raman, and so on. And that's very important because you want always be in touch with the experiment. And the more experiment you can compare with in your then the better it is. And of course, as we described, we can access complex chemical behavior. And now it's been a long time on the market, this variant of molecular dynamics and many applications. I will review only a few of them. And given the times, which where a lot of emphasis is put on applications. Here I have been given by the group at IBM this slide, which shows how some IK material has been designed with the help of these calculations, and patent has been registered, and I think this calculation has been crucial for IBM technology to progress in this direction. So that's one application that okay. So that's nice. So we don't do only argon, but we can do real things with real impact. Another calculation from the same group, I don't have time to go through it, but I mean, they are again getting prediction and result and designing new lithium battery on the basis of this calculation. Okay. Coming back to more, but nonetheless very interesting and in some way applied applications, and I just want to describe with you a calculation done by the group of Giulia Galli, now in Chicago, but at the time she was at the UC Davis, collaboration with Shell, and they were looking for an abiotic source of hydrocarbons. And the finding was that if you go in the mantle of the Earth, where there are unusual conditions of pressure and temperature, chemistry changes, and in water, under this pressure, reaction can take place, which would not be possible at room temperature, and this can lead to the formation of hydrocarbons that can then come up. And this is an important result for the balance of carbon on the surface of the Earth, which is it's an important issue for environmental and also practical purposes, since, as you can see, Shell has invested some money and effort in this. Okay. These were applications done by other people. I will come back to some things which are part of my current interest. And the first calculation, that is now somewhat old, but we keep working on the subject, is a calculation which shows how water molecules dissociate in water. So, you know, pH is due to the presence of proton. The proton, they come out from the fact that water can dissociate. There's one dissociation event, I think, per hour in a glass of water. And, but this rare event is really crucial for the property of water. And through special tricks that well, we don't have time to look into today, we can sort of accelerate the frequency with which this event takes place and study it. And so this kind of work has been done in collaboration with David Chandler in Berkeley. And he has produced this beautiful movie where we see a certain point. There is, you see, proton has moved here and here. And at the same time, there is a water molecule with a lack of a proton. And in the end, you see on one side, you have a water with an excess proton, hydronium, and you have an OH minus, which are separated, and then they go their own way until two species meet again and recombine. And of course, water is a very, very much studied problem to which many efforts have been devoted. And to study this dissociative process, of course, ab initio is an important tool because by its very construction allows the formation and breaking of hydrogen bond. But I think there is more to it. And I think ab initio water is really qualitative different from the water that you describe through effective potential. And this is shown here. If people that study protein or chemical physics, they know that if you take water and you dissolve ions, or in this case ionic salt, the property of water change. In particular, if you put sodium chloride, the diffusivity of water is reduced, and this is called structure making. If you instead dissolve cesium iodide, the diffusivity of water is increased, and this is called structure breaking. And this phenomenon is subtle, but it's extremely important in biology. If you try to simulate with available classical potential, this effect is not reproduced. If you use ab initio, the effect is well, qualitative and semi-quantitatively reproduced. And the reason for this discrepancy is that classical potential are fitted to the average property of water, GO bar and so on. But they don't fit the fluctuations. And it is the fluctuations in water which determine this effect, their subtle effect related to the distortion of the fluctuations of the medium range properties of water, which are missed by classical, but since the ab initio water contains a lot more physics in its building, so its polarizability, it has charge transfer between molecules and so on, is better equipped to describe this effect and can reproduce it to some extent. Okay. So that's one message that I thought I would give to you. So this would be what we can do and what we have done. And now, of course, we cannot sit on our laurels because there are many problems out there which are not able to solve, and we would like to solve, and problems which have to do with the size of the system that we can treat, the time scale of which we can study the system for, And of course, the accuracy, we can do density function, but we would like to do more accurate electronic structure. And also, as the complexity of the system grows, you have the problem of extracting information out of your simulation, and so a way of handling complexity at the cognitive intellectual level. Okay. I mean, we really don't have time to discuss. I would take a course all these problems and the way to go about it, but I will focus on what we've done in the last 10 years or so, and trying to ameliorate or alleviate one of the most serious problems, which is the limited time scale over which a system can be followed on the computer. And you see, the fact is that time evolution is a serial operation. So you do one step, then another step, another step, another step. The power, the slope here, doesn't come of the computer. The growth in computer power nowadays doesn't come any longer from the CPU clock time, which cannot become faster than what it is, only marginally faster, but it has to come from parallel. So you gain all this enormous computer power from parallelizing your code. The time evolution is serial, and so there is a limited way in which you can make use of this super, this huge amount of computer time. You can simulate a larger system, that's easy to do, but you can hardly go faster. I mean, there's been the show has built a purpose-built computer which can go faster than what we have, but my understanding is that is more or less at the limit of technology. And this seems to be a new second-generation computer, and that's probably will be the end of what technology can do. I mean, increase in computer speed can do, and we have to live with what we have, and also many of us don't have access to this computer, so we have to do other things. And if we look at for instance, at proteins, we see that proteins, motion of proteins involve a huge amount, a huge spread of computer times, and we can only go to easily using classical potential to simulate hundreds of nanoseconds or microseconds, but going beyond that is really painful. And if we want to simulate phenomena, many biological phenomena, many phenomena in biology take place at least on the scale of milliseconds, even more, hours, minutes. Okay, so we need to do something. But before seeing to what our recipe is for that, I will focus your attention on why there is this timescale problem. And the fact is that, I mean, if you look at the potential energy surface of a system, we often have a situation which have one minimum here, which is a metastable state, which is separated by a more stable state by a high barrier. And so the way systems go through the barrier, they sit here, they fluctuate, eventually fluctuation comes along that brings the system out over the barrier into the other minimum. At the rate for such event to take place is related through this formula. It's called transition state theory. The largest part of the the factor that more strongly affects the rate is what comes in the exponential, which is the ratio between the free energy barrier and KBT, which can be very large. And so if you start your simulation somewhere here, you will go quickly to the local minimum, will fluctuate around this minimum, and since this probability is very low, I mean, you run out of computer budget because before you see something going on the other side. So that makes our life very, very difficult. And this can be going from A to B, can be a chemical reaction, can be a phase transition between liquid and solid. It can be a conformational changes in a molecule, folding, unfolding. So really the phenomena that are really interesting. And so you want to be able to study those phenomena. The problem is that the potential energy surface in a real complex system is not the smooth double well kind of thing that we describe, but it's rather rough. This is a picture of the Swiss Alps, which I saw coming here, so in this cartoon, the problem is illustrated. Cartoon due to Chris Dalago is illustrated here. This is an artist's imaginary rendering of what the potential energy surface might look like. I mean, the potential energy surface is an object in Avogadro number dimensions, but Chris can only draw things in 2 dimensions. But this drawing captures what we expect to be the main feature of such a surface. It's a surface with many length scales and many ways of going from one well to the other. You can go from here or can go from there. So there is no easily defined transition state. There is no single path of going from here to there. And so one requires really language and tools different from standard chemical physics, where you calculate this barrier, calculate the rate. Which barrier I have to use it, and which path. That's the system. Is this path or is the other path? Okay. So we started working, as I said, now more than 10 years ago. And the first paper, which is now become rather popular, was with Alessandro Laio, then in my group. And we took 2 steps, which, I mean, in retrospect, they seem obvious, but at the time were not so common. We were not the first to think in this form, but I mean, certainly I think we took in a big way this way of thinking. So first, you see, this is, we go back to one of the points that I made earlier on. This system, complicated, that we want to study, they need a language to describe it, a language that allows to capture in anthropomorphic terms the complexity of the system. Focus our attention on what is important and what is detailed. And I've been educated as a physicist, so I'm very familiar with the notion of order parameter, Landau theory, or if you are a chemist, you know that Marcus theory, there's this solvent coordinate, which nobody knows microscopically what it is, but it's a way of describing the fluctuation, the behavior of the solvent. So it is a conceptual operation which is often done in science. So we take this point of view of describing the system in terms of collective variable. We use this collective variable, all the parameter descriptors. There are many ways of this, usually called collective variable, which we try to figure out at the beginning of a simulation to see what are the important degrees of freedom. And these are expressed in terms of this collective variable as a function of the atomic coordinate. So this will be non-linear function of the atomic coordinate, and this we assume to be the variable which are more difficult to sample. Huh? So if you have, suppose there's a molecule that has to do a conformational change, it will be a dihedral angle, a reaction between two, a binuclear molecule that dissociates will be the distance between the nuclei. That's not enough. We want to take into account also the degrees of freedom that we don't explicitly express in terms of S, and this will be done through representing the potential, the free energy surface, rather than the potential energy surface. So we focus our attention on the free energy surface, and the free energy surface is described in this picture. So P of S is just the probability distribution for the variable S. So you do the Boltzmann average, and this will give you the distribution of P of S. Take the log and multiply by minus kBt, which is the appropriate energy scale. The free energy will have a minimum when PS has a maximum. So metastable states, which are states of high probability, will appear in this description as minima in the free energy. And since you're integrating out a lot of degrees of freedom, you integrate out all these small fluctuations that there were in this picture, and you're led to surfaces which are smooth, without losing any essential physics in the process. It's a very didactical system, which will come back later on. It's alanine dipeptide. It's a small molecule which is flexible, can have different conformations, and we can study it and look for the free energy as a function of these two angles, which is also called the Ramachandran plot for those who are familiar with biomolecules. And this is the free energy, and this plot has different minima here, minima there. They correspond to different conformers, and also there is a pathway which is going from which allow you to go from one conformer to another without spending too much energetic costs. So they will give you an idea what are the minimum and roughly what is the path that the system follows to go from one minimum to the other. Okay, so that's our language, how we're going to sample, because we start from one minimum, we stay there, and never move. So, as I said, the first paper was in 2002, and we perfected, and now the original method was called, we called metadynamics, and now there's a variant which we use nowadays. It's called well-tempered metadynamic. So as the system evolves on the system, we take we add the repulsive potential, and so that the system doesn't want to go back to where it was. This potential depends on the collective coordinate. So we move, and we keep adding, and we fill the well, and the sum of the bias will be, sum of the bias that we have added will give us the free energy, apart some constant, but an important important way of, and gamma is one parameter that we can choose. If we look at the probability distribution in the canonical ensemble, so the correct one, and the probability distribution simulated in this manner, they are related. And these are probabilities which have been broadened by this gamma, 1 over gamma. Gamma is larger than 1. And the effect of gamma is shown here for alanine dipeptide. So if gamma is equal to 1, we are not doing anything. Our system remains confined in this well. If we increase gamma, the fluctuations are in a controlled way increased, and some the system can visit here. If we increase even more gamma, fluctuations are even larger, more regions of the free energy space are visited. If we let gamma go into infinity, we go back to what we did with Alessandro a long time ago. But we prefer to do that. And you see now what it works. So we said at the beginning, so going from one metastable, what brings you from one metastable state to another are fluctuations. And if you increase the fluctuations, you enhance the probability of going over the barrier and moving. This gives to this method the ability to explore large regions of configuration space, of course, provided that your choice of collective variable is a reasonable one. Okay, we'll apply to different problems, and that's illustrate also to other interests of mine. On one side, there will be biological problem, and the other also some material science, in particular having to do with nucleation and crystal growth. Why we worry about the protein? So this is a cover with science of a few years back, which was dealt in a particular paper with protein dynamics. And you know that one of the aim is going from the sequence, which is easy to determine, to the structure, which is more complicated, but not so difficult. There are many methods now. And then to the dynamics and the function. And it's the dynamics, besides the structure, dynamics influences the function of the protein. So understanding the dynamics is important to understand the function of the protein. Structure is given to you by X-ray. In many cases, or NMR, dynamics, there are not very many tools to study it, and so MD can be of great importance. And that's one protein, that's a kinase that we studied a few years back. And this is it's far from being a rigid molecule. There's a cavity here, which is it's an enzyme, so the cavity can be open, and so the ligand can come and be catalyzed. But there is another state of this kinase by which this loop, this green stuff, slowly closes, and it goes into a new state, forms what is called an alpha helix, and you go from one state which is open to a state on-off, and regulating this two states. If you have this is not regulated properly, then you have all sorts of diseases. And so understanding this mechanism is important to design drugs that might cure diseases associated to malfunctioning of the kinase in your body. And just not to show that we can only do movies, we can get hard numbers using this method. For instance, the important parameter which is for interaction between, say, a drug and the target protein, is the binding affinity. And we can see this little red molecule to go inside and out on the time scale of the simulation. And through the way it goes inside and out, under the action of metadynamics, we can calculate the affinity, which is something that people measure experimentally, compare with. Okay. As I said, another side of my group is to see especially nucleation and crystal growth, with the idea pretty soon to be able to control the self-assembly of nanostructures. And that's one example, which I like it very much. This is work that has been done in collaboration with the experimentalists in Zurich, Professor Marco Mazzotti, and where he studied the precipitation of crystals from solution, crystal of urea, and how to control it. And we can predict what the shape of the crystal can be. And so so if you have form crystals out of a solution of urea in water, you form these elongated crystals, which are shown here. That's our prediction. This is the experiment. If you change the solvent, ethanol, the shape changes. If you go to methanol, another change. So prediction and experiment. Then acetonitrile you got here. Then if you add another substance, an additive, which is called biuret, you can still modify the things. And if you start with acetonitrile and you add this additive, you go to a totally different shape, which is this triagonal prism. So you can go from here to there. And this is important about for processing of the materials, but also for delivery of drugs, because the shape influences a lot the ability that we have to deliver drugs. Okay. I'm going very, maybe it's running late, so let me skip this thing here, because otherwise we go overboard. Okay. And we conclude with the very recent development, of which we are proud, which I can only treat like advertisement. So metadynamics, as I've described so far, is a method to explore configuration space, see which metastable states are possible, and what is the difference in free energy. So free energy meaning that we have not only the difference in enthalpy, but the difference in entropy, which is more difficult to get. But we have not yet done, we have not gone from this exploration to real time. Now we have a method for doing that. It's a very recent physical review letters. And we can calculate, for instance, we have seen in the previous talk, if you have a drug and a protein, we can calculate the binding energy. But now we can also calculate what is called the K-off. So the rate, once it's here, how fast it escapes, which is also an important parameter for drugs, because you don't want it to be stay too short or too long. It has to be just right. And and this can take from milliseconds to hours. And that's a little movie, which just flash it, but a movie which doesn't want to move. Okay, so that's, you can see the little thing the surface of molecules. It escapes from its binding site, and there are a few cohort, a small cohort of water molecule that helps this object to get out. If we look here, so that's we look only. This is the binding pose. So see, this little molecule is tightly bound to this residue of the protein, and as it escapes, there are some water molecules that come about, hydrate the ligand, help it to escape it, and go into the solvent. I will not explain this. The last one, but similar things we can do from Lennard-Jones and calculate nucleation rates, but I will stop here because I overrun my. If you want, I can tell you. I mean, I will give other talks, so those who are interested on the specific subject, they can come to my talks, and thank you for your attention.